So who are you?
My name is Sanjeev. I'm a student at the RI, and this is my friend, David
Hey.
Choi.
Hi there.
Hi, my name is David.
So I'm a third-year PhD student, and welcome to the RI. So
And where are we?
we are in the floor A of the RI in Neil Simon Hall
In Carnegie Mellon,
in
right?
Carnegie Mellon.
So I'm not in Redmond anymore.
No.
They let me out sometimes. It's great.
That's cool.
And what are we going to see here?
We're going to see a lot of cool robots, a lot of cool technology, and it should be very exciting.
Excellent. Cool.
So
And what do you do here?
So this is the medical instrumentation lab, and if you can follow me.
Cool.
I don't have.
And you don't mind me filming you, right?
Nah, that's fine.
Okay,
What
cool.
is this going to be used for?
It'll be up on Channel 9, actually. channel9.msdn.com.
Really?
Yeah.
Great. I don't know if I'm wearing the right
Yeah, what's this Northwestern stuff?
shirt. But yeah, unfortunately, I don't have any working demos. But
Okay.
I'll just explain a couple of things that are going on in the lab. First, over here we have a project called Heartlander. It's a device that can walk on the heart. It's the surgeon can drive this robot on the surface of the heart.
Wow.
And the advantages of that is, well, a lot of heart surgery right now has a surgeon opening up the chest and the rib cages, and a lot of the new technologies are moving towards minimally invasive. So faster recovery time for the patient and things like that. And so this is one way. So it just requires a small incision in the subxiphoid process.
Yep.
And the robot then can crawl up. This is the model of the heart.
Right.
And we've done tests on pig hearts with it, and it's been successfully able to walk on the heart. It uses suction, vacuum suction.
How big is this thing?
So here's one of the prototypes. This is actually not my project, so I don't really know that much of the details, but this is one of the prototypes.
Wow.
And
it
there's
uses suction to move along?
Yes, vacuum suction and cable. It's cable driven, so that when the cables are pushed and pulled, you can actuate the front part of it.
And does it have a camera on it? What would it do when it's
right.
crawling on the heart?
Yeah, there have been some test runs with cameras inside. It's kind of difficult to get cameras that are that small and with that are clear as well. But in the future, we'd have like needles or maybe even like some more fancy tools that the surgeon can use to manipulate. And the great thing about this is that normally the heart is beating if you're trying to do an operation on it. So they'll either like stabilize part of it, or they'll maybe even stop part of that and slow it down. But in this case, since the robot is actually walking on the heart, the motion of the robot is relative to the heart is zero. So it appears to the surgeon that it's not really moving.
Wow.
So yeah, so that's an advantage of this type of thing.
That's really killer.
Yeah. Let's move on. The other major project.
What are the challenges in developing a technology like this? I mean, what kinds of skills do you need, and how is it different than somebody who was here 5 years ago, for instance?
Right. So this project, I think, started a few years ago. I think a lot of the challenges in the beginning have been mechanical in nature. Just trying to figure out like how to best get suction, and some algorithms on how to know when the foot is firmly planted on the heart and things like that. And in the end, I mean, we're gonna have to deal with like kinematics and how to plan like a path maybe on the heart and do that maybe partly autonomously. Right now, it's joystick driven by the surgeon. So I mean, those are the kind of things in the future. But for now, I think a lot of the technical difficulties have been like mechanical in nature.
How long do you think it'll be before this kind of technology actually gets used on a real life person?
Well, that's hard to say. I'd say, I don't know, 5 years, 10 years, something like that.
Okay.
I know that's a pretty big window, but yeah. I wish the other person was here.
right.
The person that was working on this.
What's his or her name?
His name is Nick Petronic.
Okay.
So the other major project in this lab is a device we call Micron, and it's a handheld surgical tremor canceling device. So essentially it does three things. First, it can sense its own motion. Then it can distinguish between the tremor and the desired motion of the surgeon.
So if a surgeon has a little bit of a shaky hand,
right, exactly.
it can dampen that?
Right, exactly. And so then the third thing is that it moves the tip in an equal but opposite way from the tremor. So if the hand is moving like up and down, then the tip would move down and then up, so that the end position of the tip is actually not changed or altered. So
this probably makes brain surgery a little bit better.
Yeah, so there's a few applications. Neurosurgery is one of the applications. Another application is eye surgery, where the surgeon, one of the things that the surgeon can't really do with his hand right now is to go into one of the vessels, and if it's clogged, it puts some anticoagulant in it. But because the tremor is about the same size as the veins. So this device would help with that process, which is a cause of a lot of blindness in Americans.
Right. Does this have applications in other technologies? For instance, the camcorder I'm using has this one doesn't use optics, but it uses digital movement if my hand moves, and it tries to dampen that.
Right.
But would the same kind of technology be able to use in other things?
Definitely. And I think there are already some cameras that use accelerometers. So the way that it senses its motion is using accelerometers.
Okay.
And right now magnetometers. But yeah, you can put accelerometers and piezoelectric stacks in a camera and move the lens. And I think there are companies that are working on that right now. Another application is if you're manipulating small cells. Biologists have to do that with quite high level precision, and so this device would help them inject things into cells and things like that. Yeah, I can give you a quick. So we ran a little test, and so on the left, on the right side is the needle. It's the tip of the needle that's attached to this device Micron.
Okay.
And I'm going to start and on the left shows the displacement of the needle.
Right.
And what I'm doing now here is simulating a tremor-like motion. It's a sinusoid, and at 10 seconds, I'm going to turn on the capabilities of the tremor canceling, and you can tell that the motion has been attenuated.
So right there, it turned on, or I'm sorry.
No.
Okay.
Sorry, I'll play it again for you.
Oh, okay.
So basically, it's the needle is moving about 80 microns peak to peak in a sine wave, and right about 10 seconds, it goes down to about 50% of that. So about 40 microns. So you can tell from the graph and the video that the tremor is slightly reduced.
That's really cool.
Yeah.
It'll save some lives. Stuff's important.
Yeah.
Did you see Celestron, by the way? It has at CES, I just saw it, has a sky scope that uses similar technology to this, where it senses what part of the sky you're looking at and tells you what you're looking at.
Okay.
And it's using gravitational and magnetic and also accelerometers to tell where you're looking.
Units,
and it actually, you can tell it, hey, show me the 10 coolest things in the sky, and it'll actually tell you where to point your scope and look at.
Okay.
And it's using similar kinds of technologies to this.
Right, definitely. A lot of things use this kind of technology, like from missiles to like mobile robots and things like that. So.
Very cool.
Yeah. I think that's pretty much it. Yeah, it's good.
Very cool.
Okay.
Thank you very much.
Thanks a lot.
Thanks for showing us a
Yeah,
little
no
bit.
problem. Wait, where is this going to be online today, or?
Oh, no. A couple of weeks. I'll probably send you guys the video clip so you guys can see it first. Cool, thanks.
Thanks a lot, Dave.
Blur out there.
No.
That's I didn't even think about it. I didn't know.
I don't know either. That's cool. Okay. All right, man. Thanks, Dave.
Northwestern gets some free advertising.
All right.
So what's next?
Did you enjoy that?
That's really neat stuff.
Yeah, it is. So right down the hall here, there's another lab.
Okay.
And this is more like conventional robotics that you might be more used to. So hopefully you'll get the chance to operate a real robot. So remember again to ask them before you come.
Yep.
So, all right. This is Tom.
Cool.
Tom. Hey, Tom. This is Robert.
Hey, do you mind if I film you?
Yeah, sure. Go
Okay, cool.
Nothing in here.
And what's your name again?
Tom.
Tom, and what's your last name?
Lowers.
Lowers. And what do you do here?
I am a graduate student in robotics working in educational robotics. So that's my project.
What a lot of fun.
We're going to be demoing it.
Cool.
That's actually the most recently completed project. I guess I should give you sort of a brief description of the lab. This is the Mobile Robot Programming Lab, although we're looking to change that name soon. we've been working basically for the last few years in education and robotics, and so we ran a course at CMU West that's in the Bay Area a few years ago, in which high school students put together some TrikeBot robots, and it was actually a relatively advanced course for high school students.
Yep.
And we found that especially like the things that people thought they would learn, mechanics, programming, they learned. But things, we actually asked them, what do you expect to learn? And things like teamwork and identification with technology, these things they found, they didn't expect to learn these things, but they found that they actually ended up learning those things.
What kind of skills do you need to be a student here? I mean, if
a graduate student in robotics, or... Well, I mean...
How do you get here? That's a good question.
Okay, so I think there's actually a wide variety of paths, because robotics is so interdisciplinary. We have people coming in here from math, from physics, from computer science, obviously, from electrical engineering, mechanical engineering. So really, sometimes even from, biomedical engineering. So we really have like a wide variety of paths into robotics, just because robotics encompasses so many things.
Yeah.
So you can find something to work on with many different given backgrounds.
Very cool.
So it's good to just have a general science and technology focus, I think, to your undergraduate career.
Now on your screensaver over here, I see the Mars robots. Was some of that done in this lab?
Well, so these Per robots, and in fact there's a whole army of them over there, and some more over there, were deployed to museums, the Smithsonian Air and Space Museum, the Exploratorium, and a few others that I can't remember offhand.
I think I saw one of these in the Mars Museum at NASA Ames.
Yes, that's where one of those is.
It was a cool little exhibit for a while.
So they were deployed at the same time that the Mars rovers landed, and so sort of to capitalize on all that interest. And they were run by, I don't know, we stopped counting after the first 2 months, but there were 200,000 users in the first 2 months that ran these robots. They run for about 3 minutes per exhibit, so it gives people, a decent amount of time to use the exhibit, but it moves them along too. And actually, we have the exhibit running on this computer.
Okay.
So, so it says, click the button to begin your mission. So I'll just click. And then it takes a panorama. And, in the museums, they actually sit in a Mars yard.
Yeah.
And it's kind of hard to see from the exhibit what the Mars yard looks like from the actual kiosk. So you really want to convey the concepts of both teleoperation and also the slight amount of autonomy that the Mars rovers themselves have. So rover is standing by. So what you first do is you click on the panorama image to select a rock.
Okay.
So let's go for this rock over here. So it tells you that you're going to turn 88 degrees, so the robot will turn that amount, but then you also have to select a distance that you expect to go there. And in the museum version, this little map actually looks like the Mars yard like a satellite view of the Mars yard. So let's say we go about 1 meter. That looks about right. Then you just tell it go. So what it does is it turns that 88 degrees. And it's actually a pretty neat, locomotion system, because you have these omnidirectional wheels here, and all 4 of these wheels are mounted on servos so that they can spin in 180 degrees.
Right.
So you've got quite a few, this thing can actually drive sideways or drive forward while turning and stuff like that, so it's a little bit neat.
Now, what kinds of things did you guys learn by building these here?
Well, a little bit about the technology, this has 3 different circuit boards in it, and that was because the current robotics technology, you need a high-level processor for wireless, and then you also need a bunch of low-level stuff to deal with the servos and the motors and so forth. And actually what it's doing right now is it's imaging the rock. So did you see the little UV glow? And so what it does is it says, here, mission completed, purple glow indicates signs of life. So it shows you that, your rock shows signs of life. But what you may not have noticed when it was when it was going towards the rock is, when I steered it, it was actually at about this angle. And it turned towards the rock autonomously. So what we're trying to convey is not just that you teleoperate the rover, but the rover has a little bit of internal intelligence too to sort of correct for small human mistakes. So you give it a general direction, and it'll find the rock in that direction. So it's more than just driving a remote control car.
What kinds of algorithms is it going through to decide on the direction?
I think generally...
And did you write some of the algorithms?
No, I didn't. So
Okay.
I'll just give you what I think is the high-level information. But generally, so there's obviously the camera in the head here. There's also a IR distance sensor, which tells you how far you are to objects. And what it's basically doing is it's scanning the environment for objects that are about as high as this rock.
Okay.
So it's very simple. And it's very easily broken in, an environment like here where there's lots of objects as high as rocks. But in the Mars yard, we've sort of set it up so that really the only things it'll focus on are the rocks.
Excellent.
So it's just looking for things that are rock height and rock shaped.
Right. Now, what are these guys working on over here?
So this is actually the next project. And part of that had to do with what we learned from the PER and also from the TriCbot course, which was the high school course. So this controller here will soon be released, and actually, you may not want to mention this until mid-March.
Okay.
So, but this controller will soon be released, and it is a high-level and low-level controller all in one package. So you can do wireless information as well. You can connect to a wireless network, stream USB webcam information over that network, and also control a bunch of low-level things like motors, servos, sensors, and so on. So what you have with this controller is the core of a instantly teleoperable robot at a very low cost, right? Because you can control it over any wireless network. The USB webcam will allow you to see what it sees, and then it has all the necessary stuff to control a robot.
Right.
So
now, what's the goal of the lab here? Is it to design something that'll be a product someday, or is it to learn about technology that you might apply later on when you get into industry? Or
I would call it multifaceted. So, a lot of the things we do are a little bit more product-oriented than other, labs, but at the same time, we are not the ones who we're not interested in necessarily spinning that off into a company.
Okay.
For example, that board was designed by a corporate partner of ours to the specifications that we asked for. But what we're interested in is developing a community of users who want to use this technology, and then also to develop curriculum around the technology. So, for example, for high school courses or like college computer science courses. So using robotics as a tool for education instead of using robotics to teach about robotics, which is a little bit, there's a subtle difference there that's important.
Is there a place that you want people to contact you? Do you have a weblog or a website? Or
we have a preliminary website on Turk, which I can send to you, which is cs.cmu.edu/tilde-turk, T-E-R-K. We're planning a more community-based website which people can actually go to and look at some recipes, so look at different designs we've developed to build robots around this controller and so on.
Yeah.
That should be released also mid-March. So again, it would be good. Oh.
It works. It's tethered, so don't I won't do any more.
So in terms of release, we're thinking like mid-March. So
Discovery here in action.
Yeah.
We'll get you the video so you can improve it, by the way, and all that fun stuff. That's what our Channel 9 rules is. Everybody who is on the video gets to approve it and say that it has to be held for a certain date or whatever.
Okay, good.
So who are you guys, actually, since you're here?
I'm Chris Bartley. I'm one of the other developers on Turk.
Okay.
I'm a recent new hire.
Excellent.
Yeah, as of a couple days ago.
And what kind of tools are you using to build the software that runs this thing?
I use, it's all in Java. This stuff I'm doing at least.
I work for Microsoft.
Interview's over then.
You're using Windows, though, so you're cool. I'm just kidding. He's a Linux guy, right?
I use a tool called IntelliJ IDEA.
Yeah.
Best IDE I've ever used. So sorry if you don't like to hear that as a
No,
Microsoft guy, but totally changed my life. Love it. But so that's what I'm primarily developing.
What was it again? I'm sorry.
IntelliJ IDEA.
IntelliJ IDEA. Very cool.
It's good stuff.
And what kinds of things? What makes you wake up in the morning and come here?
Well, desire for a paycheck.
Oh, you get paid to have fun with them?
Yeah,
I gotta get
it's
a
one of
gig
those
like
things.
this.
I can't believe they pay us to do this. You know, this is great. It's just fun working with a great group on an interesting project, and it's exactly what I was looking for when I was looking for a job. I knew I wanted to do Java, knew I wanted to do robots, preferably something with the school, something that doesn't kill people. Yeah, because there's a lot of military robotics that just doesn't interest me.
Yep.
So for me, it's perfect.
Very cool.
Yeah.
What do you think you're going to do after this gig? Are you going to take this technology and run a big company? And
Well, I don't know about all that. No, I'm fairly small on the totem pole here with the project, so it wouldn't be mine for the taking. But no, I have no plans to leave and go somewhere else.
Cool.
So I'll stay as long as they'll keep me.
Excellent. What's the coolest thing about this? What if another developer walked in? What would you show them first?
I don't know that I could show them very much of anything. This is the first time that I've ever actually had anything talk to the robot, so maybe Brian can answer that better.
And what's your name?
Brian Dunleavy. Yeah.
Great. And what do you do on this project?
I'm in charge of the software development for it, so I've been the primary hacker on the project since its inception, and yeah, everything below the hardware, more or less.
So what would you be if another geek walked in? What would you show them about this? That's cool.
I think the hardware is pretty sweet. We've got everything packaged together in a nice little system and a lot of capability.
Why is this important at this time? I was here when it first moved, right? That's pretty interesting that I'm here. Yeah. What's important about this? What in 3 years are people going to be talking about this moment in time, or?
Hopefully not that moment in time. We've actually had it running around before. We're doing a slightly different web interface now. But, in 3 years, I hope it's in schools. Yeah, we'll know in 3 years.
Well, thanks. Cool. Thank you very much for spending some time with us. It was great. And I'll send you the video so you guys can see it.
Okay.
Cool. Thanks. Thank you very much.
See ya. Thanks, Phil. Thanks, guys. Nice meeting you.
All right.
Wasn't that cool?
That was cool.
Yeah, really nice demo.
Yeah.
So now we're going to a lab that's more, it's again different from the stuff we've been looking at. It's more manipulation, so it's trying to build robot hands and technology for robot hands.
Okay.
So give me a second now while I find it because my memory is a little jacked. So, let's see. Yeah,
Yep.
Hey Ravi, how's it going?
Do you mind if I film you?
No, no problem.
Great. And who are you?
I'm Ravi
What's your last name?
Balasubramanian. Ravi
Okay.
Balasubramanian.
And what do you do here?
Still on.
Yeah.
I'm doing my PhD in robotics, working with Professor Matt Mason and Professor Al Rizzi.
Okay. And what kinds of things do you do every day?
Yeah, right now you're in the manipulation lab, and we have a few projects going on here. Let me first talk about my project. This is called the rocking and rolling robot. It's
Okay.
a extremely simple robot. It's just a hemisphere with two legs attached to it. But the key thing about this project is that the legs never touch the ground. So you may wonder why we built such a robot so lame. It has two legs, but it never can never walk. So the idea behind this is that what happens when a turtle is flips over? Can it still locomote? So one way is you can wiggle the legs hard enough so that you tumble over, and then the robot can use its conventional locomotion strategy. Yeah. What we also found out was that the robot can locomote just by wiggling its legs and choosing an intelligent phase relationship between the two legs. For example, we were able to show that if you wiggle the legs up here,
Yep.
you can move laterally. If you wiggle the legs down here, rock back and forth, and if you wiggle the legs 45 degrees off the horizontal, you move in a counterclockwise circle.
Wow.
And the basic idea behind this motion is that by wiggling the legs, you produce pitch motion,
Yep.
roll motion, and yaw motion simultaneously. And the way you control the locomotion is you control the relationship between leg motions and the roll, pitch, yaw oscillations, both in amplitude as well as the phase relationship. And that interacts with the contact constraints, basically the constraints that it rolls back and forth without slipping, and that it can yaw at its contact point. So basically when you combine these three aspects of the locomotion, we see this locomotion which we call legless locomotion.
Interesting. Are you going to demo that for us? Does that actually
unfortunately, it's not plugged in here.
Okay.
So that's one thing. So some of the related work to this project are satellite locomotion. So when you have, and basically this is floating in space, and you wiggle the legs,
Yep.
right? You can reorient the body. Right, so this is how they reorient satellites in space, either using manipulator arms or using reaction thrusters.
Okay.
Right, this has no thrusters, but it has these arms, and that's how we are making use of to control the body orientation.
Wow.
That's one thing, but this problem is. The rocking and rolling robot problem is more complicated because there's gravity, right?
Yep.
So that means you rock back and forth, and
Yeah,
also
up in
there are the
space you don't have gravity.
You
right?
don't have gravity. So,
How do you test something when it doesn't?
so there are many
I guess
ways.
you have simulations, but
You have simulations, but they also test it in water,
okay.
or they have nice balancing mechanisms that cancel out gravitational effects.
Okay.
So a lot of NASA's research projects, they use such mechanisms.
Okay.
Or if you can just look at it in a planar sense, right, you can just have a frictionless ad hoc table and you can study these things.
Very cool.
That's there. So this is my project. Before there was a grad student by name Sid Srinivasa
Okay.
and a few more collaborators. They built this robot which is called the Mobiplator.
Okay.
Mobiplator stands for mobile manipulator, and the idea is that you have a desktop robot which can move things around on your robot and on your table, maybe even clean up things when you're not at your desk. So they were able to show that with these sticky wheels, you can manipulate paper on the table.
Oh wow.
Right.
I'll
So
take a picture.
sure. Maybe I put it on the ground.
Oh, that's cool.
So they were able to show that they can manipulate paper and move, pencils around on the table, and so that is this project. There's one more thing that one of our grad students worked on. It's called robotic origami, and that student has since graduated. But the idea is, supposing you have a shape.
Okay.
Like this, right? And now I unfold this origami. How do you learn? How can a robot learn how to recreate the shape?
Okay.
Right. So there's first of all there are many folds, right? But also you need to understand how to fold it. What is the sequence? So he looked into planning strategies for multiple fold origami, and some of the things that this robot did is this envelope there, and it also did a samurai hat, but I don't have an example right here.
Okay.
But the key idea you can see, which they used, was they used one of these, I forget what's rollers, yeah, to flatten out paper. Right.
Yep.
So the idea was, you see a suction cup,
Yep.
right? So one of these suction cups would pick up a side of the paper, right, and move it over, right?
Yep.
And then it would, while I'm sorry, I'm not doing a good job here. Okay, so what it would do is it would move one of the edges, right?
Yep.
And clasp it
Ah.
right here using these arrow ducts,
Yep.
right? So once you clasp it, you can use the other hand. You can use this hand now
Yep.
to hold the other side, and then bring it over, and then create the crease.
Wow.
There's a movie of this on our website, and it probably does a much better job than I can
I'm
do.
sure.
So that is a project that he worked on.
What kinds of things are you? What kinds of things do you find you learn by building these things? For instance, are you building software for these? Or
Right, I build software, and you learn a lot of math, you learn a lot of physics, a lot of theory, right? So the basic idea is you're trying to understand what are the natural, laws that our mechanical systems are governed by, right? And we noticed in this rocking and rolling robot project, or legless locomotion project, that you can actually locomote without even your legs touching the ground, by finding the relationship between angular momentum, the timing, the phase relationship between the two legs. So that is something that is very important. We also build a lot of simulators that help us understand these things, because it's not easy to understand what's going on in a sequence of motions just from, even though you have data, it's very difficult to see it. So you build simulators, and then you can slow down the motion, speed up the motion, and then so you can really understand what the key thing is there. There's one more project that I'm working on, but it's not. We are just starting to set it up.
Okay.
So here is our small yard where we have a robot stuck in a ditch.
Yep.
Right? And the idea is, what are the, let's say you have a car, right?
Yep.
That's stuck in the ditch, and you want to figure out what are the wheel torques you should apply to get this car out, right? There's a standard problem of a car trying to get over a hill, of a vehicle trying to get over a hill, and there are many AI, like artificial intelligence, like techniques to look into this problem. But we are going one step further, and we are saying, what if we want to get this robot out of this ditch without slipping? So you have these tires,
Yep.
right? And as it's rocking back and forth, right, the gravitational, force acting on the system changes, because right here, right, the normal gravitational force is going to be way lesser than down here.
Yep.
Right. So because the gravitational force along the slope is lower, right, you have lesser traction, right?
Yep.
So the idea is, what is the best way?
Or is it the other way? Wouldn't the gravitation?
So
Actually,
when you're up here, the normal gravitational force is lower.
Is lower or higher?
Lower.
Okay.
Because, so this is the gravitational force, right?
Yep.
As the angle changes, the gravitational force is, you have only a component of that along the contact normal.
Okay.
So it's
The
lower.
wheels don't stick as much
Yeah.
when it's like that.
Right.
That's what it's
Yeah.
So the idea is then can you...
I understand. I got it.
I mean, that's why you slip
Yeah.
on a slope and not on the ground.
Got
Otherwise
it.
you will slip on the ground.
True. Okay.
So the idea is, can you find, a sequence of wheel torques and brakes that manage this reduction in traction as you're moving up and down the slope.
Yep.
So that you don't slip, and then you can still get out.
Now that has implications for the car industry, right?
Exactly. So we are looking at the problem of not just wheel torques, but also in terms of active suspensions. So if you can move your car mass up and down, right, you can control the traction force also. So you have a gate between wheel torques and active suspension forces.
Interesting. Very interesting.
Yeah.
You could also design wheels that swing out and get behind the car. Wouldn't that help push it up?
You mean moving chassis.
The actual axis, and so it, because the wheels right now are here. What if you could move the wheel here,
Right.
and then as it comes up the slope, it would have still wheels that are more on the flat part.
Yeah, that's possible too, but
Makes it more expensive.
it's more expensive, right? Even having an active suspension increases your car cost by, I don't know, $3,000, $4,000, right? So with existing systems, how can you find better solutions?
Yeah,
Right.
it's a fun job.
Yeah, it's a lot of good work.
Well, thank you very much.
Yeah. Well,
What kind of software do you write for these things? Like the rocker? How many
rocker
lines
is
of code?
extremely. So the simulation is pretty complicated. Complicated in the sense, the number of lines of code is probably about, I don't know, 500 or so.
Okay.
It's not that long, but the thing is, we ask the computer to generate the equations of motion for us.
Okay.
Right, these natural laws that the system has to behave according to. So those equations of motion are like at least 1,000 or 2,000 terms in that range. So if you just take a particle mass and you move it along a straight line, right, that system has about 2 or 3 terms.
Yep.
Right. So this system, rocking and rolling robot, has about, I don't know, 2,000 or 3,000 terms. So to understand those terms, what the contribution of each of these components is not easy, and that's why we write software. So there are a lot of mathematical modeling softwares that are there, but the key contribution is not in writing that software for this lab. Right. The key contribution is to understand the natural laws that govern us.
Got it. Wow.
The physical laws, basically. And this work, this rocking and rolling robot work, has, I would say, we are the first to discover this sort of locomotion. Nowhere before has this sort of locomotion where you have an under-actuated system. This is what it's called. You have just 2 legs which are actuated, but the robot has way more, degrees of freedom. It can move in way more directions. So for such a system, we are one of the first to find, the equations of motion and find what are the key contributors for that.
Very cool.
Yeah.
Thank you very much.
You're welcome.
Thanks
Your
for
name,
spending some
please? I
time.
didn't
I'm
know.
Robert Scoble from Microsoft, from
Okay.
Channel 9.
Nice to meet you.
Thank you.
See you later.
Thanks, Ravi.
Yeah, see you later.
I hope you enjoyed that.
That was awesome. A lot of fun work going on
Yeah.
here.
So now we'll be going to the Field Robotics Center, which is like this large place with a lot of robots.
Okay.
There'll be a lot of interesting stuff, but we're only going to see one of it, so we'll be walking right through. So
Okay.
we don't have much time, so I know you'll feel like stopping and looking at each robot. We have to go to the people who are waiting for us. So
Okay.
we'll just walk past really quickly, and if you have any questions, you can ask me.
Cool.
But we won't be stopping.
Okay. Is there anything you don't want me to take video of?
So I mean, you said that you guys will have us approve it, right?
Yeah.
Before.
Yeah.
So I think that's fine. I don't
Okay.
think it's a big deal.
Cool.
We won't have time to look at all those robots, but you should just kind of just
I'll take a look
them
at it.
as we go past. They're all really cool.
So since we're going on an elevator, shut off for a second.
So, yes.
So here we go. Thanks.
Field Robotics Center.
Robo cranes. Wow.
These are some of our best robots that are autonomous and go on their own out into deserts and things like that.
Yep. Sorry. Really cool stuff. And segways.
Is it okay if he films your stuff?
Yeah, sure.
Okay, fine.
Do you need more time?
No, I'm just going.
Okay.
Cool. I'm Robert Scoble from Channel 9 at Microsoft.
Hi.
So who are you?
Christina.
Yeah.
Nice to meet you.
And what do you do here?
I work with Segway RMP's robotic mobility platform, along with Brenna.
Very cool.
This is our robot. Right now she's filling the tank so we can kick.
And who are you? I'm
So,
sorry.
hi, I'm Brenna Argel. I'm a second-year PhD student in the Robotics Institute. Christine and I are in the same lab, we're the same advisor.
And it looks like you get to tear apart segways and do fun
right.
things.
So what we do with the Segway, so RoboCup, so yeah, I can show you how it balances.
Okay.
So what it is it actually balances as an inverted pendulum, and the whole control sequence to have it balance is a black box that Segway only has access to. And so what we get when we get the Segways is something that looks like this, which is one of ours that isn't built up yet.
Yeah.
And we can send it velocity commands and turn angles, and that's it. And so when we run the Segway, we have a laptop on the back here that runs 2 pieces of code, one which interfaces with the Segway directly to actually give it motion commands, and one which does all of our higher level processing in terms of like vision, and deciding what sort of soccer actions to execute. So this is a soccer playing robot. What we have actually added to the robot, its primary sensor is vision.
Yep.
So it has a camera right here, which is mounted on a pan tilt unit, so it can be moved around. It also has a camera down here, which is a wide angle lens, and that's stationary. So it can't see as far, but it can see wider.
Okay.
It then additionally has a catcher, which we use to grab the ball.
Okay.
The catcher in general in most of our code is set off by these 2 IR sensors, which will presumably only be activated when the ball is right here, and then it sets the catcher down.
Wow.
And then this is our kicker. And the kicker is powered by a tank of compressed CO2, which is back here, which you saw me filling when you came in.
Okay.
This model, so there are 2 models of Segways. You can see this is a smaller one.
Yep.
This is the P series, this is the I series. The I series is we actually also have a pre-recorded body motion where it kind of bucks to do a kick. That this model actually can't handle that because it's too small. So, do you know anything about RoboCup?
No.
Okay, so RoboCup is actually, there's an international league. And there's also, we actually now have U.S. Open games too. So we have a competition that's just in the U.S. There are multiple different robotic leagues. There's simulation leagues. There's the small Sony Ibo dogs. There's a league called the Small Size, which are robots about this big. There's also a mid-size, and there's starting to be a humanoid league.
Where do you learn more about that?
RoboCup, I think robocup.org.
Okay.
We'll have it. Certainly, if you go to our lab's webpage, we have a lot of information on that. Our lab actually has. We used to do the simulation league. I'm not sure if we're doing it this year. We definitely have an IBO league, and we have a small size league, and we have a Segway league. So the difference with the Segways in robot soccer is that it's actually humans and robots coordinating together as teammates.
Okay.
And so the way that we do that is we normalize them across platforms, and we have the humans ride the Segway HTs over there.
Yep.
And so they have similar capabilities. The human cannot kick the ball with its foot. It has to use the Segway. And by doing that, we hope to sort of normalize them across platform and really have them be equal teammates. No one's master-slave in either direction.
Interesting.
So that's one of the major research questions with doing Segway soccer particularly. And RoboCup soccer is just in general a great way to get robots to have to coordinate together autonomously and in an adversarial environment. So.
Wow. That sounds like a lot of fun.
It is. It's a lot of work and a lot of fun.
Now, in terms of what you guys, what you do during the day, is most of your time spent coding? Is most of your time spent on machinery?
It sort of depends on what time of the year we're in. So
Okay.
right now we're starting to prepare for the U.S. Open, which means that we're going to spend a lot of time with the robots, and that means you spend most of your time testing actually, and in doing that you tweak your code, but as far as writing completely new code, I'd say that takes less time than testing, definitely.
Yeah.
And then that goes hand in hand with the hardware. So the more you test, the more you realize where your hardware is deficient or
In terms of
what you
software
wanna do.
tools, what are you guys using?
In terms of what?
Software tools, yeah.
So we've pretty much wrote it all ourselves, and it's in C++. So, yeah. And so a lot of it is actually, a fair amount of it was borrowed from the IBO team. So we've been doing other RoboCup soccer in our lab for years, and so we sort of had a certain code base built up. And so some of it we could definitely borrow from them, which was very helpful.
Do you see any sort of commercial impact of this eventually, or?
So Sony definitely is interested in our IBO code, and we collaborate with them. I'm not sure what they intend to use it for, and actually, my lab might know what they intended to use it for. I just don't particularly, so
Yeah.
because I don't work with those robots. certainly Segway provides these the Segway platform in a robotic form, so they must, because when we get it from them like that, they're intending it's going to be for research purposes. So they obviously have an interest in it. In terms of its actual applications within society yet beyond this, I'm not sure I can think of a direct example, but certainly it's a lot of people are interested, and the funding comes from a lot of different places. So I think that it's something that will have application in a lot of areas.
And how do you two work together? What parts do you share, or what skills do you each have that are different?
So she is kind of my mentor because she's a year ahead of me.
Okay.
So we do some similar things. We're both working on software right now, and we'll both be doing kind of similar things in terms of testing and writing and tweaking software and whatnot.
Mm-hmm.
So.
In terms of we actually just segregated our tasks for what we're going to do to prepare for RoboCup. And so Christina is going to be working on a lot of the team coordination, and so getting robots to talk to each other and getting the humans to coordinate with the robots as well. And I'm going to be doing more of the single robot stuff, so we need to work on navigation, being able to not only detect obstacles but drive around them, and then also just building up more single robot soccer skills. So.
Cool. Can you demo it?
Yep, we
That'd be
certainly
cool.
can.
Here, I'll get over here.
Do you want to drive it forward with it? Right now we're just joysticking it forward to position it better. So if you actually wanted to, I don't know if you're interested at all in doing the go through, but this is some of the software that our advisor wrote. So here we can give the commands there. This is a robot-centric view of the world, so each ring represents 1 meter out from it. Okay. So you can see that red dot is corresponding to it being able to see the soccer ball in front of it. Yeah. This is a balancing, and there's actually a much more we can do. If we have this show up, this is what the pan tilt camera is seeing. It actually sees it in color. It just sends it over the network in black and white. Okay. But that takes up a fair amount of bandwidth, so we normally keep it turned off unless we need it particularly. So that's sort of the interface that Christina's going to go through.
Does it use the images on the camera to sense where it is, or is it using...
Right now we're not using localization at all. That is certainly something that the IBO team does and that we would like to do eventually, especially because when you're on a soccer field, they color code the corner posts, and so you can determine where you are in the field because of that. Right now, we aren't doing that yet, and it actually wasn't necessary when we were at the U.S. Open last year because the field was much smaller than it was supposed to be, the space that we were given, and so you could always see either of the two goals, and you could orient yourself based on that. But it certainly does take the images from the camera and then process the world based on that. So right now, it's going to track the ball, and the way that it identifies the ball is a combination of color. So the ball needs to be orange, and the surrounding color needs to be ground, which here is sort of a random gray. The code is actually, you can imagine the code actually runs much better on a soccer field because the ground is green, and you don't see green with an orange speck around other places very often. Yeah. But here, in this environment, there's gray sort of everywhere, and then orange specks or red specks, and so it's much more difficult to try to concretely say what is the ball and what is not. But right now it's tracking the ball, so you can see it'll follow it with its camera as I move it around.
Oh, the camera's following it.
The camera's following
Got
it. So yeah,
Let me actually get over here.
So it is tracking it as I move it, and then it's alright. Yeah, come here, it's fine. And And then right now, if I make it so that the robot loses it, it will go into a search mode and it'll start turning around, so you might want to take a step back.
Okay.
But here, it lost it. And so now it's searching for the ball. And then when it finds it again, it'll track it again. And so now it found it, and now it's tracking it.
That is cool.
It lost it, and now it's tracking it. So, we'll run something now that is just a demonstration on how it can follow the ball. So it's going to run up to the ball and stay a certain distance from it. It's not going to go up and grab it completely, but then I'll be able to move around and it'll kind of follow me.
Okay.
Yeah, and so you're welcome to get close to the robot. Just remember it's dynamically balancing, so it might not...
I'll stay behind you.
Yeah, it might not behave as you expect it to.
Keep the researcher between you and the robot.
That is sort of our...
I only have to outrun you, right?
Yeah, right. Chase ball. All right, so here it comes. It's just going to stay there because it won't get closer. And this, we really have our speeds turned down just because we're in sort of a tighter environment. But especially if we take it outside and have a lot more space, it's really, the Scoble platform is pretty impressive in how quickly it can turn and chase the ball.
Oh, they can go, what, 20 miles an hour? Or 16 miles an hour?
I thought that the top speed on this one was 8. I'm not sure
8?
about the newer models.
Okay.
And this is the more robust model of these two. So. All right.
Hours of enjoyment.
Yeah. So now we will be able to, if Christina wants to stop that, we'll actually do, we'll show you the robot catching the ball and kicking it. So, yeah, if you want to do catch, kick, two, and then raise them. So it's just going to kick it straight forward.
Okay.
Normally, if we were in a soccer game, it would look for a target to kick it to. So it can either look for its human teammate, which I'm not sure we have. We have markers. Oh, I don't think we have any right now. We on the Segway HT, the human one, we normally have a marker that's 3 color bands, and that's how it identifies its teammate. Or the goals are big colored goals, so it would, in general, choose to shoot to one of those. But right now, since we're just demoing, we don't have any colored stuff set up. It's just going to kick it straight forward back to me.
Okay.
So, is it ready? Okay. So right now, it sees the ball, and it is aiming towards the ball, though you can't. Maybe I can get you to show it. Yeah.
Yep.
So it's aiming towards the ball, and then I'm going to kick it towards the ball, or towards it. It'll catch it, and then kick it forward.
Let me try that again. Keep the camera on the ball. That's excellent.
So, oops, okay. And now Christina's going to have to stop it because, as you might guess, it will just continue to follow the orange ball. And so, the success of testing this or the safety in testing this is dependent on the human actually kicking the ball well, which I certainly don't all the time.
Great.
So,
does it have any predictive capabilities? Like, does it try to figure out where the opponent is trying to kick the ball, or?
So right now we don't have that in at all at that higher level. It certainly tries to track the ball based on velocity. It's not just straight vision. We have trackers, and actually the tracking system we're using right now was developed by another graduate student, Young Gu, and and it actually uses it's called a multimodal tracking system, and he has 3 models of the way that the ball can be behaving. One is that if it's actually trapped within the catcher, one is if it's moving away from it, and one is if I think it's stationary but the robot's moving towards it. And so, and that works much better than the previous tracking system that I had used. So,
very cool.
Thanks.
This is a lot of fun. Who knew you could play soccer with a robot?
Yeah, right. Well, you should go to our website because actually, right now, this league's very new. There's no international league. We've only done 1 series of games. But the other teams that have been playing for a long time, it's very impressive what they're able to do in terms of soccer and strategizing with other teammates and everything. So if you go to our website, I can write it down for you.
Okay.
You can at least read about our other teams.
Sure.
Yeah.
Now, do you play other schools or?
The only other, so right now there was only one other opponent at the U.S. Open, and they are actually a research institution called the Neurosciences Institute, and they're in San Diego. And it was actually very interesting. Their approach to building a robot was entirely different from ours, and our strategy on the field was to a robot make all the decisions, and the human just kind of played off of that. And theirs was the opposite. The human made all the decisions and then told the robot what he was doing, and they had a voice recognition on the robot, and the human wore a headset. And sort of in terms of what we're trying to do with this league, neither is quite correct. We actually want them to be equal. We don't want either robot or human to be dominating. And so, yeah, but it's a very challenging question, and you kind of need to tailor the rules to enforce it, and that's also hard because you don't want to tailor them too specifically, and yeah, it's very interesting.
How many years before a robot can keep up with Mia Hamm or Pele? Or?
Yeah, right. So that's actually the intent of the entire RoboCup League. By 2050, they want the champions of RoboCup to take on the champions of the World Cup, and so of the Human World Cup. And so, hopefully by 2050.
Very cool.
Yeah. Thank you.
Well, thank you for spending some time with us.
Oh, no problem.
And thanks for the
My
tour.
pleasure.
I'm almost out of tape, so do we have another lab?
No, it's very done.
This is awesome. Thank you for giving me a tour of Carnegie
I'll
Mellon's.
walk you up to thanks so much
Yeah,
for asking
you're
me
welcome.
to.
No problem.
Yeah. Thanks. And I'll stop the tape here. Did you have something else for me to see?
No, I'll just walk you back up.
Okay, great.
All right.
Thank you very much for this great tour.
Thank you so much for coming.